Hello everyone, Mrs. Patel Dane here. Now we're on topic 7.11, solubility equilibria. So at the end of this lesson, you should be able to calculate the solubility of the salt based on the value of KSP. So I just want to give you guys an idea of what we're looking at here. We have this glass that has a whole bunch of calcium deposits on it, and now we're adding some substance onto it in order to help us remove it. So eventually, over time, the glass will look like this. So when we're thinking about like what happens with solubility, we're thinking about like a substance, a solid, dissolving in solution. So here we're looking at, in this case, NaCl and silver nitrate. So what I want you to do for this one is to figure out what the products are, as well as thinking about particle diagrams. So go ahead and pause this right now. So here we have to make sure that we break up NaCl, since it is aqueous, into its ions, Na plus and Cl minus, and the same thing with silver and the nitrate ion. Next, we'll figure out what will actually come together and what will dissolve. So we know that all group 1 metals will dissolve, as well as nitrates and ammonia. So in this case, we have sodium, which is a group 1 metal, as well as nitrate. They won't come together as a solid. However, silver and chloride will. So we will show that we have Na plus ions and NO3 ions plus AgCl at the end. So when we put this together, we have Cl minus plus Ag plus at producing AgCl solid. So when we're thinking about a particle diagram, we have Na ions with Cl minus ions, the silver ions with the nitrate ions, and then at the end, we'll still have the sodium ions and the nitrate ions, but the silver chloride will come together as a solid. So the equation down all the way at the bottom is a net ionic equation. So we're going to look at what KSP is, and then show the equation for dissolving AgCl right at the KSP expression, and then see if you can figure out how to determine what the concentrations of the ions are based upon its KSP value. So KSP is anytime you have a solid dissolving in a substance. So that's called the solubility product. So in the case of silver chloride, we have silver chloride solid is in equilibrium with silver ions and chloride ions. The KSP expression eliminates any solids and liquids, so we're just left over with the ions. So in this case, KSP is equal to the silver ion times the chloride ion. So if you get the chance to figure out the next problem, go ahead and do that now. So here we have again the KSP of AgCl is 1.6 times 10 to the negative 10th. We want to figure out the molar concentrations of the ions. So we can start out by putting it into a rice table. We have AgCl solid is in equilibrium with Ag plus ions as well as Cl minus ions. We also know that AgCl, since it is a solid, won't have anything to do in the rice table, so it's kind of just negligible. We can see, though, however, silver plus and chloride ions, we have nothing to begin with, but we are adding a plus X for each one of them. And then we're writing out the KSP expression again. So KSP is equal to the silver ions times the chloride ion. And then we'll plug in. So we have KSP, which is 1.6 times 10 to the negative 10th, is equal to, in this case, X squared. So we'll take the square root of 1.6 times 10 to the negative 6. And this, 1.6 times 10 to the negative 10th, excuse me. And so that gives us 1.26 times 10 to the negative 5th. Since we have two sig figs at the top for our KSP, we will see that we have two sig figs for our ions. So we know it should be 1.3 times 10 to the negative 5th. Make sure you have molarity in there, is equal to Ag plus Cl minus. So if we think about a small KSP or a KSP less than 1 versus a large KSP, which is greater than 1. So I want you to pause right here, and what would make a small KSP and a large KSP? So we're thinking about this equation that we had from before, AgCl solid is in equilibrium with Ag plus and Cl minus. We know that its KSP value is Ag plus and Cl times the Cl minus. So if we have a small KSP, it favors the reverse direction, meaning you're probably going to have more AgCl and more of the reactants. If we have a large KSP, on the other hand, that means that we favor the forward direction. That means we have more product. So I want you to try out this problem. The lead ion concentration of PbCl 2 is 1.62 times 10 to the negative 2 molar. Calculate the KSP. So we will, again, there we go. So we're going to go ahead and put it into a Rice table again. And so we have our equation PbCl2 solid is in equilibrium with Pb plus 2 and 2Cl minus. And don't forget that for PbCl2, it is a solid, so we won't have anything for its initial, its change, or its equilibrium. For Pb plus 2 and 2Cl minus, we do know that the lead ion concentration of PbCl is 1.62 times 10 to the negative 2. So that's actually representing our X. And so we know that we have our X here. We can figure out what our Cl minus is because we just multiply it by 2 to give us our 2X. So when we're solving for KSP, we still use our Pb plus 2 times Cl minus 2, or Cl minus to the square root, the square. And then we'll go ahead and plug in our values from before. So as we plug it in, we have 1.62 times 10 to the negative 2 times 2 times 1.62 times 10 to the negative 2. Don't forget we have to square that because the Cl minus is squared. So plugging that in, we end up with 1.70, and we need 3 sig figs. So 1.70 times 10 to the negative 5th. Remember, it is KSP, so it doesn't have a unit. So go ahead and try this problem. So we have 2 chlorides of copper, CuCl and CuCl2. The KSP of CuCl is 1.7 times 10 to the negative 7. Molarity of CuCl2 is 5.2 molar. Which one's more soluble? So as we do the problem, we're going to pick one of them. So let's take CuCl and put it into our Rice table. So we have CuCl solid, and we will dissolve that into its ions. So we have Cu plus 1 and Cl minus 1. Again, it's negligible for the CuCl. We start with a 0 initial concentration, then the change is plus X for each, and then we'll plug that into the KSP. So the KSP is equal to the Cu plus 1 times the Cl minus, and then we'll put in our values, 1.7 times 10 to the negative 7, and we have 2 x's, so we might as well square them, then take the square root. So we have the square root of 1.7 times 10 to the negative 7 gives you, in this case, 2 sig figs, 4.1 times 10 to the negative 4th molar. And so that's how much, pretty much the molarity or the concentration of those ions for both Cu plus and Cl minus. So we'll show you a little bit bigger here. When we're comparing how much will dissolve of CuCl versus CuCl2, we can see the molarity of CuCl is 4.1 times 10 to the negative 4th molar, whereas the molarity of CuCl2 is 5.2 molar. So we see that CuCl2 actually has a greater molarity, hence it'll be able to dissolve more and be more soluble. So at this point, can you calculate the solubility of a salt based upon the values of KSP? I want to thank ChemMix for chemmix.org for our wonderful little demos at the beginning.